Here in problem 1, we want to determine the absolute extreme values of the function on an interval, and the interval that's given is between x equal minus 1 and x equal plus 2. When you're looking at extreme on an interval, the things you want to consider are the values of f of x at the critical points. That would be where f prime of x equals 0 or it's undefined. The first derivative of the function here is defined for all values of x, so we need to look at the critical points where the first derivative is 0. And the other 2 points we need to look at are the endpoints, f of 1, f of minus 1, and f of 2, and then see which is the largest and which is the smallest. So let's first of all look at f prime of x, and that is equal to e to the x minus 1. Notice that it's equal to 0 when e to the x is equal to 1. Solving this equation by taking the natural logarithm of each side, we take ln of e to the x equal ln of 1. So x is equal to ln of 1, which is 0. So x equals 0, and f of 0 equal e to the 0 minus 0 equal 1 is critical value, 0 and 1. Now we need to check the endpoints. By the way, you don't have to check the concavity here, but you can see that this is probably going to be a minimum value because the concavity, the first derivative of x, is equal to e to the x. So f double prime at 0 is equal to 1. It's more than 0, so it's concave up. I sort of draw a little thing like this, which tells me it's a local minimum. And it's also possible it'll turn out to be the absolute minimum. But we at least know now it's a local minimum. Now we need to check the endpoints. F of minus 1 equal e to the minus 1 plus 1 is equal to approximately 1.3678. And we'll check f of 2 is equal to e squared minus 2. It's approximately equal to 5.39. Comparing all these values, we see that this is a max. In fact, it's an absolute max. And we see that the local minimum we calculated is also an absolute min because it's larger, it's smaller than 1.3678. So we see the answer to this is answer C. Minimum value is 1 at x equals 0. The maximum value is e squared minus 2 at x equal 2. Second problem, we want to find any extreme values of this function. Notice it's a polynomial, so it's going to, and it's a third order, and it's going to go to plus infinity as x goes to plus infinity, and it's going to go to minus infinity as x goes to minus infinity. So it's not going to have any absolute max or min, but it could have a local max or min. So let's take try to find the critical points. First derivative is 3x squared minus 6x equals 3x times x minus 2. It equals 0 at x equals 0 and at x equals 2. Let's test these 2 points using the second derivative test. The second derivative is equal to 6x minus 6. So the second derivative at the first critical point is equal to minus 6, which means it's concave down, which means it's a local max. And if you look at the second derivative at the other critical point, you see that it is 12 minus 6 is more than 0, so it's concave up, so it's a local minimum. So x equals 0, y equal 1. It's a local max. X equal 2, y equals minus 3. By the way, you get the minus 3 by plugging in the 2. Y at x equal 2 is equal to 8 minus 12 plus 1 is equal to minus 3. So it looks like that answer is going to be C. The next problem, we want to look at this piecewise defined function and determine if it has any local extreme values. Well, for x negative, the function is a straight line with a slope of minus 1. And for x more than or equal to 0, it's a quadratic function. And it's a parabola, and it's concave down. And so we need to look, first of all, at the interface between the two piecewise defined segments. X equals 0 is a potential critical point. Now, let us graph this function. As we said, to the left, it's a straight line with a slope of minus 1. So we can say as x approaches 0 from the left, f prime of x is equal to minus 1. Now, graphing the function to the right, we see a parabola, as we said. Here the function is 3 plus 2x minus x squared. So as x approaches 0 from the right, f prime of x equals 2 minus 2x. And y prime as x approaches 0 from the right then is equal to 2. So no, they're not the same. And so f prime does not exist at x equals 0. So you can see that this is a local minimum at x equals 0, y equals 3. It's probably the first part of our answer. Now we need to look at the next critical point, and that would be here where the derivative would be 0. Just look at that function, f prime of x there is 2 minus 2x equals 0 at x equals 1. And without even doing the second derivative test, you know that that is a local max. Because it'll be concave down, just go ahead and do it. F double prime of x, see, it's equal to minus 2, it's less than 0. So it looks like of all the answers we have here, x equals 0, the derivative is undefined, it's a local minimum, and the value is 3. And at x equals 1, the derivative is 0, and it's a local max, and f at 1 happens to be 3 plus 2 minus 1 equals 4. So answer B. Problem 4, we want to look at the potential application of the mean value theorem. We're looking over an interval from minus 2 to minus, from minus 3 to minus 2. And we want to see if there's a point in between minus 3 and minus 2, a point C, such that the first derivative at C is equal to f of b minus f of a over b minus a. Well, first of all, f of minus 2 is equal to minus 2 squared plus 4 times minus 2 plus 2 equal minus 2. F of minus 3 is equal to 9 minus 12 plus 2 equal minus 1. So f of minus 2 minus f of minus 3 over minus 2 minus a minus 3 is equal to 2 minus a minus 1 over, this is 1 down here, is equal to minus 1. So we want to find a point such that the first derivative, by the way, the first derivative is going to be 2x plus 4 equal minus 1. So we get 2x equal minus 5 and x equal minus 5 halves. And so that is the point C where the mean value theorem holds. And the answer is C. Problem 5, we want to determine the intervals on which the function f of x is increasing or decreasing. In this particular case, we were already given the first derivative of x. We know it's increasing if f prime is more than 0. It's decreasing if f prime is less than 0. We're already given the derivative f prime of x is equal to x to the 1/3 times x minus 5, and that's equal to 0 at x equals 0 and x equals 5. So we need to break the interval from minus infinity to plus infinity into 3 parts, from x equal minus infinity to 0, x between 0 and 5, and x between infinity and 5. And now calculate f prime at minus 1. We need to have a test point between minus infinity and 0. The easiest place to check is at minus 1. So that's minus 1 to the 1/3 times minus 6. Well, the cube root of minus 1 is minus 1, so this is more than 0, so it's increasing. And then a good point to check is x equal 1, so x to the 1/3 times minus 4 is less than 0, because that's 1 to the 1/3 times minus 4, so it's decreasing. And then finally, let's check x equals 6, and we have 6 to the 1/3 times 1 is more than 0, so it's increasing. So looks like the answer is C, decreasing 0 to 5, and then increasing minus infinity to 0 and 5 to infinity. Problem 6, we want to find the intervals on which the function is increasing or decreasing. Here again we have a third-degree polynomial that's going to go to plus and minus infinity as x goes to plus and minus infinity. So we need to basically look at any critical points. It's not going to have any place where the first derivative is not defined. So let's look and see where the first derivative is 0. Well, the first derivative, k prime of x, is equal to 3x squared minus 48 equals 3 times x squared minus 16 equals 0 at x equal plus 4 and at x equal minus 4. So we break the timeline, or the x-axis, into 3 intervals from minus infinity to minus 4, from minus 4 to plus 4, and from plus 4 to infinity. First test point should be between minus infinity and minus 4. I would pick x equal minus 5 and test the first derivative, and we get 3 times 25 minus 16. It's clearly positive, so it's increasing. And then we'll test x equals 0 for the next interval, and we get 3 times minus 16 is less than 0, so it's decreasing. And then test x equals 5, and we get again 3 times 25 minus 16, clearly more than 0, so it's increasing again. And so the point minus 4 and f of minus 4 is a relative max. That would be minus 4 and 128 if you plug in the minus 4. And then the point 4 and f of 4 would be a relative min, and that would be 4 and minus 128. So these are the answers. Problem 7, we want to find again the intervals on which the function is increasing and decreasing, and look at the function's extreme values and see if there are any that are absolute. First of all, the first derivative of this function is the first times the derivative of the second, which is e to the minus x over 3 times x times the derivative of u, which is minus x over 3. So that would be minus a third, plus the second times the derivative of the first, which is just going to give us simply e to the minus x over 3. Now we would factor out e to the minus x over 3 and get 1 minus x over 3. This equals 0 only at x equals 3. So we divide the interval up between minus infinity and 3, and between 3 and plus infinity, and then test the derivative. We'll test 0, plugging in 0 into the derivative. We get f prime at 0 is equal to e to the 0, which is 1, times 1. That's more than 0, so it's an increasing function. And then we will test, looks like test 4 would be the easiest one, and we get e to the minus 4/3 times 1 minus 4/3. E to the minus 4/3 is positive, and this is negative, so this is less than 0, so it's decreasing. So we have a function that looks like this, and so at x equals 3, y is equal to 3 e to the minus 3 over 3, which is 3 over e. So we come up with the conclusion that point 3 and 3 over e is a relative max. And because everything is decreasing this direction is going down. As you go to the left, this would be also an absolute max. Problem 8 is to look at this function and locate the local extrema and identify the intervals where the function is concave up and concave down. Now, just going to assume that you can look at this graph fairly easy and read the values off of it. First of all, you see a relative max here, and that looks like x is equal to minus 3 and y is equal to 4. and it's concave down. And as best you can tell, it looks like it's concave down from minus infinity to 0. Notice that the relative minimum occurs here. As best you can tell, that would be 3 and minus 8. And it's concave up between 0 and infinity. So that looks like problem. The answer to problem 8 is number A. I would just stop in here for a second to see if there's any other thing we could point out here. Okay, problem 9, we have a function y equal 2x cubed minus 9x squared plus 12x, and we want to sketch the graph and show all the local extrema and inflection points. This means that we want to find, first of all, the critical points. And in this case, this is a polynomial, so it has no place where the derivative is not defined. So we want to find out where the derivative is 0. So calculating the first derivative, we get 6x squared minus 18x plus 12 equals 6 times x squared minus 3x. We'll factor 6 out. We want to set that to 0. That means that 6, and now we're going to factor it, times x minus 1 times x minus 2 is equal to 0. So the critical points are x equal 1 and x equal 2. Either of these could be relative min or a max, and we'll determine which they are by taking the second derivative and doing the second derivative test. So let's take the second derivative, and let's just go back to the original function. That would be, the second derivative would be 12x minus 18, and we need to calculate the second derivative at the critical points. We'll first take x equal 1. The second derivative at x equal 1 is equal to 12 minus 18 equal minus 6. That's less than 0. That means it's concave down. That means since it's concave down, we can see this would be a relative max. So at x equal 1. So the value of y, the function at x equal 1, is equal to 2 times 1 cubed minus 9 times 1 squared plus 12, and that equals 5. So we know that the point x equal 1 and y equal 5 is a relative max. Now let's check the other critical point, which was x equal 2. Second derivative at x equal 2 is 24 minus 18 equals 6. That's more than 0. That means it's concave up. So at x equal 2 is a relative min. Now calculating the value of the function y at x equal 2. That is equal to 2 times 2 cubed minus 9 times 2 squared plus 12 times 2. If you calculate that, it's equal to 4. So we know that the point x equal 2 and y equal 4 is a relative min. Now it asks for inflection points. And then we'll actually sketch the graph. The second derivative has to be 0 at an inflection point. And we know it has to have an inflection point because it goes from being concave down to concave up. So let's set the second derivative equal to 0, and that is 12x minus 18 equal to 0 at x equal 18/12, which is equal to 3/2. The value of y at 3/2, just by plugging it in, and I'll let you do that, you'll see that the value of y at 3/2 is equal to 9/2. So the point 3/2 and 9/2 is an inflection point. Now, starting to graph this, you can put in the calculator. And you will see that, well, at x equals 0, the y value is 0. At x equal, let's put a little scale here. This is 2, 4, 6, 8. So at x equal 1, then let's do the scale here. 2, 4, 6, 8, 10, 12, and 14. So at x equal 1, the value is 5. So that would be this point. At x equal 2, the value is 4. And that would be the min. And if you graph some points, you will see a function that looks like this. And actually there's a prettier graph on the next page. But here's a max, a relative max, and here's a relative min, and looking on the next page, you'll see a little prettier graph. It's answer A. Relative max at 1 and 5, and a relative min at 2 and 4. And as we said, an inflection point at 3/2 and 9/2. So the inflection point is right here in the middle between the min and the max. And that is number 9. Okay, folks, we need to analyze this graph. It shows a portion of the graph that is twice differentiable at all x except at x equal p. And you can see why it's not differentiable, because we have point here at which the derivative from the left and the right are not the same, and therefore the derivative is not defined. And it asks us to, at all the label points, classify y prime and y double prime as positive, negative, or 0. Okay. Now, first point, A, is easy. We would say the first derivative is not defined, and the second derivative is not defined. But at point B, we look at that point and you know that that looks like a local minimum, so the first derivative would be 0. And since it looks to me like it's concave up, the second derivative has got to be more than 0. Looking at point C, at point C, the first derivative has got to be more than 0, because that is certainly not a local minimum, and it's increasing. It also looks like it's going from concave down, concave up to concave down. So it looks like an inflection point. That means that the second derivative is equal to 0. So it's an inflection point. Now D, it looks like the first derivative is equal to 0. And it looks like it's going from concave down to concave up. So we would think that the second derivative was equal to 0, and that is an inflection point. See, it's up here, it's down here. Now point E, it looks like the first derivative is more than 0. It's increasing. And it looks like the second derivative would equal 0, because it looks like it's going from being concave up to down in concavity. So it's an inflection point. Then finally, not quite finally, but almost finally, at F, it's a local minimum. So first derivative is equal to 0, and the second derivative has got to be less than 0 because it's concave down. And then finally, point G, it's decreasing, so the second derivative is 0. Looks like it's roughly a point where it's changing concavity from being from being down to being up. So this is an inflection point. And this computer is getting a little slow here. We have problem 11. We want to find two positive numbers whose sum is 16, such that the product of one number and the cube of this other number is a maximum. So let's let x equal the first number, and y equal the second number. And the function we want to maximize is f equals the first number times the cube of the second number. So you want to make this a max. Now, notice we've got two variables here, and we need to eliminate one of them. Now, we're told that the sum of the two numbers, x plus y, is equal to 16. Solving for x, we get x is equal to 16 minus y. So now we can plug this value of x into the function and get 16 minus y times y cubed is equal to 16y cubed minus y to the fourth. Now, this is what we want to maximize. And to do this, we want to take the derivative of f with respect to y, or f prime. And that would be 48 y squared minus 4 y cubed. Now, this can be factored into, we can take 4 y squared out, and we're left with 12 minus y, and we set that equal to 0. So the first solution to this is y equals 0. That's obviously not a solution. And y equals 12. It turns out that is the solution. If y equals 12, then x is equal to 16 minus y equals 16 minus 12 equals 4. So the two numbers are 4 and 12. Now, that's answer A. You could also look at this function and graph it. And if you graph it, you will also find out that if you graph it for y between 0 and 15, that you have to get the right window. But you'll see that at y equal to 12, the functional value is 6912. You can actually do this on your calculator and find the maximum value, and it's 6,912. And that is the maximum of the first number times the cube of the second number. So the answer is A.
In problem 12, we're trying to find the optimal dimensions of a shipping container or a box that has a square end. We want it to have, by being a square end, this end could be x by x. In other words, it's square. And we want to find the dimensions that will give the box the largest possible volume. So we want to also find the length of this box. And there's a constraint on the box that the sum of its length, which would be y, plus its girth, which is the distance around, must not exceed 102 inches. So right away, we can say that the length of this box plus the distance around, which would be 4x, is going to equal 102 inches. In other words, it could be less than 102, but obviously to get the maximum dimensions and get the maximum volume, you'd like to let it be 102. And to get the maximum volume, we then need to maximize V, which would be the length times the width times the height, and that would be x squared times y. That's the 3 dimensions of this box. So we have 2 equations here. We want to maximize the volume given the constraint that y plus 4x equal 102. Notice you can solve this equation for y and get y is equal to 102 minus 4x, which we then can put in the volume equation so that we get volume is equal to x squared times 102 minus 4x. And so that the volume is equal to 102 x squared minus 4x cubed. To find the optimal value of x, we then would take dv dx, which is 204x minus 12x squared, or I'm sorry, minus 12x squared equals 0. And factoring out an x, we get 204 minus 12x times x equals 0. And we get a solution that x equals 0, which is of course a trivial solution. And the other is that 12x equal 204 and x equals 17. Now, you can show that this is a maximum value. Notice you can get v double prime is equal to 204 minus 24x, and evaluating that at x equal 17, you get 204 minus 24 times 17 is going to be less than 0, which means it's concave down, which means it's a maximum, which is what we thought. So the dimensions of the box are going to be 17 by 17 by the length, which is y equals 102 minus 4 times 17 equals 34. So the dimensions of the optimal box would be answer A, 17 by 17 by 34. In problem 13, we have a line segment that's going to be the hypotenuse of a right triangle that's 19 units long, and it runs from x and 0, which would make this dimension x, to the point 0 and y, which would make this dimension y. And we want to show that the area of the triangle enclosed by this segment is largest when x equals y. Well, the area enclosed by the segment would be 1/2 the base, which is x, times the height, which is y. And we want to maximize this. Notice that we need to find an expression for x in terms of y, and we immediately see that this can be written as x squared plus y squared equals 19 squared, which is the Pythagorean theorem. And so we could solve this for y and say that y is equal to the square root of 19 squared minus x squared. Substituting this in for the y, we get that the area is equal to 1/2 x times the square root of 19 squared minus x squared. And rewriting this so we can take the derivative more easily, we get 19 squared minus x squared to the 1/2. Now, taking the first derivative of a with respect to x and factoring the 1/2 out, we get the first times the derivative of the second, which would be 1/2 19 squared minus x squared to the minus 1/2. And not forgetting the chain rule, we got minus 2x here, plus the second part of the product rule, which would be the second portion times the derivative of the first, which is 1. We now get that dA dx is equal to, simplifying, notice you can cancel out the 2's here, and we're going to get minus x squared over the square root of 19 squared minus x squared plus 19 squared minus x squared, the square root of, all divided by 1. Combining these terms, we get, and we have 1/2 out here as a factor, 1/2 times minus x squared plus 19 squared minus another x squared all over the square root of 19 squared minus x squared. And this equals 0. And we immediately see that we get 2x squared is equal to 19 squared. So x is equal to 19 over the square root of 2. So that's the optimal value of x. Now, substitute this in the formula for y, and you get y is equal to the square root of 19 squared minus x squared equals the square root of 19 squared. X squared would be 19 squared over 2, while this is equal to this the square root of 19 squared over 2, which is equal to 19 over the square root of 2, which lo and behold is equal to x. So we prove that x is equal to y for the optimal size of the triangle. Now, problem 14 is a geometric problem. We want to make a rectangular enclosure subdivided into 4 pins by 3 parallel partitions. And we need to build this enclosure with a total of 500 meters of fencing. That's all we have. And then we want to know the dimensions which will maximize the total area. So first of all, we need to draw the rectangular enclosure. And it's going to be subdivided into 4 sections with 3 parallel partitions. Now all of these sections are supposed to be equal. We're going to let the height of each of these be y, and each little pin is going to have a width of x. And we're told that the total amount of fencing that we have is going to be 500 meters. Notice that means that 8x, notice count all your x's up, and you got 8 of them, plus 5y is going to be equal to a total of 500. And the area which we want to maximize is equal to 4 times x times y. Each one of these pins has an area of x times y. So the total will be 4xy. Notice this has two variables, and so we need to eliminate one of them, and I'm going to eliminate one of them by solving for 5y is equal to 500 minus 8x. So y is equal to 100 minus 8/5 x. Now I'm going to substitute this in the area equation, and then I will get A is equal to 4x times y, which is 100, minus 8/5 x. And this is equal to 400x minus 32x squared over 5. Now we want to find the max of this, so we need to take A prime is equal to dA dx, which is equal to 400 minus 64x over 5. And we want to find the critical point, setting the derivative equal to 0. That implies that 400 equals 64x over 5. And so 64x is equal to 2000. And x is equal to 2000 over 64. Now, the length of the top then will be equal to 4x. And so that's equal to 4 times 2000 over 64. And if you calculate, that's 125 feet. Now to get the y, we plug back in to our other equation. Y is equal to 100 minus 8/5 x equal 100 minus 8/5 of the x value, which is 2000 over 64. Doing a little cancellation here, we get 8 down here. This goes into this 400, and we get that y is equal to 50 meters. So the answer is answer E. 50 meters by 125 meters gives you
the dimensions of this pen that gives you the maximum area.
Problem 15, we have a rectangular field that's being closed on 4 sides. The issue here is 2 opposite sides have a cost of $7 per foot. The other 2 opposite sides have a cost of $3 per foot. And the field is supposed to have a dimension of 620 square feet. We want to minimize the cost. So let's draw a picture. Rectangular field. Let's say that the dimension of the width of the field is X, and the cost that side of the field, let's say, is going to be $3 a foot, and the other side is going to be Y, and it's going to be $7 a foot. So we can say that the cost function is going to be 3x plus 3x plus 7y plus 7y. So the cost is 6x plus 14y. And the area is equal to the length times the width, which is x times y. And that area is supposed to be 620 square feet, meaning that y is equal to 620 over x. So we can substitute this into the cost equation and get that the cost is equal to 6x plus 14 times 620 divided by y, divided by x. Taking the derivative of the cost with respect to x, we get 6 minus 14 times 620 over x squared. Set that equal to 0, and you get that 6x squared minus 14 times 620 all divided by x squared equals 0. The only way this could be 0 is for the numerator to equal 0. So we get that x squared is equal to 14 times 620 over 6. And we get that x is equal to 38 feet. That's at $3. And substituting y, that's approximately 38. I believe it's actually 38.03. And substituting in for x and getting y, we get y is equal to 620 over x, and that is equal to 620 over 38.03, and that is 16.3 feet, and that's at $7. So it looks like the answer is B. Problem 16 is to find out how many units of a product you need to be produced and sold in order to yield a maximum profit. The concept here is that your profit, your P of X, is equal to your revenue minus your cost. To maximize your profit, you set the derivative of the profit equal to 0, so P prime is equal to R prime minus C prime. If that's equals 0, then you want your R prime to equal your C prime. So that is fairly simple here. R prime is equal to 70 minus X which equals C prime, which is 9. So X is equal to 70 minus 9 is equal to 61. So that was an easy one for a change. Problem 4 is using L'Hopital's rule to find a limit. Notice if you substitute x equals 0 in the expression, you'll get 0 over 0, which is an indeterminate form. So we can use L'Hopital's rule to say that the limit as x approaches 0 of sine of 2x divided by the tangent of 4x equals the derivative, the limit of the derivative as x approaches 0, the derivative of the denominator or the numerator, which is 2 cosine of 2x, don't forget to use the chain rule, divided by the derivative of the denominator, which is 4 secant squared of 4x. And you can write this as a limit as x approaches 0 of 2 cosine of 2x over 4 times 1 over cosine squared of 4x. If you substitute in now, you get 1 down here and 1 up here, and you get this equal to 2 over 4 equal to 1/2. The answer is B. Number 18 is using L'Hopital's rule again, and here we say that the limit of 16x squared minus 8x minus 6 over 18x squared minus 6x plus 8 as x approaches infinity is equal to the limit as x approaches infinity. Notice the indeterminate form is infinity over infinity, so L'Hopital's rule does apply. So we take the derivative of the numerator, we get 32x minus 8 over 36x minus 6. We still get infinity over infinity, so we do it one more time. And we take the limit as x approaches infinity, the derivative of the numerator, which is 32, derivative of the denominator, which is 36, and we get 32 over 36 equal 8 over 9, which is answer D.
Okay, problem 19 asks us to find the limit of this expression as x approaches 0, and we're going to use L'Hopital's rule to do this. If we first plug in 0, try to calculate this by plugging in x in the numerator and denominator, we get cosine of 0 minus 1 over 0 equals 1 minus 1 over 0 equals 0 over 0, and it's indeterminate. So we want to use L'Hopital's rule, which says that the limit as x approaches 0 of cosine of 7x minus 1 over x squared, if it's first indeterminate, that is equal to the limit as x approaches 0 of the derivative of the numerator, which is
minus 7 sine of 7x divided by the derivative of the denominator, which is 2x. And you plug in here and you get minus 7 sine of 0 over 2 times 0 is equal to 0 over 0. It is again indeterminate. So let's go one more time and see if we'll make it. L'Hopital's rule says that we can take the limit as x approaches 0 of the derivative of the numerator, which is going to be minus 49 cosine of 7x. Derivative of the denominator is 2. And this equals minus 49 cosine of 0, which is, of course is 1, divided by 2. So the answer is minus 49 halves. And we got this fairly easily. The answer is A.
Problem 20 is just to find the general antiderivative, and you remember the symbol for the antiderivative of a function is just the integral of the function dx. That's the notation. All we have to do here is take the antiderivative of each individual part of the function, and that would be 5x to the 4th over 4 minus 5x squared over 2 plus 2x plus c, and the answer is A. Okay, problem 21. We're given the acceleration, initial velocity, and initial position of a body, and we want to find the position of the body at time t. So we're given that the second derivative of s, which is the acceleration, is equal to 18. Therefore, the first derivative, which would be the antiderivative of the acceleration, would be equal to 18t plus some constant c1. That is equal also to the velocity. And we're given that v at 0 is equal to minus 7. This implies that c1 is equal to minus 7. So we can write that the first derivative of the position is 18t minus 7. Now taking another antiderivative, we'll get s is equal to 9t squared minus 7t plus another constant c2. This is the position, and we're given that s of 0 is equal to 3, which implies that c2 equals 3. And so you can see that the position function is 9t squared minus 7t plus 3, which is answer A. The next problem is to find the antiderivative of the expression in the integral sign. And one of the things to remember is always think a little bit before you start trying to work a problem. It's often worthwhile to rewrite the problem. Notice that you can write this as the integral of x to the 3/2 power plus x to the 1/2 power divided by x squared dx, which is equal to the integral of x to the 1/2 plus x to the minus 3/2. And now we're going to take the antiderivative of each individual term, and that's going to be x This is x to the minus 1/2 here, folks. Notice that x to the 3/2 divided by x squared is x to the minus 1/2. I think I've got the signs right on everything else. So this is going to be x to the minus 1/2 plus 1 divided by minus 1/2 plus 1 plus x to the minus 3/2 plus 1 divided by minus 3/2 plus 1 plus a constant. Simplifying this, we get 2x to the 1/2 minus 2x to the minus 1/2 plus c, which is 2 times the square root of x minus 2 divided by the square root of x plus c, which is answer C. Okay, problem 23 is a rocket science problem, but it's really not all that hard. As everybody knows, the acceleration of gravity on Earth is minus 32 feet per second. And we're looking at a rocket that's launched at t equals 0 from the ground, but we give it a little help with a new warp drive that's capable of imparting an extra acceleration of 42 feet per second, thus overcoming gravity and yielding a net acceleration of plus 10 feet per second at t equals 0. In addition, an initial velocity of 1,000 feet per second is also imparted by the warp drive. So we want you to write an equation for the velocity v of t and the position s of t of the rocket. So, and then to answer the question, what is the position of the rocket in miles, and round to the nearest mile after 1 day. So we note that the net acceleration is equal to 10 feet per second. So we can say that the acceleration, which is the second derivative of the position, is equal to 10. So now, taking the antiderivative, we can see that s prime, which we know is also equal to the velocity, is equal to 10t plus a constant. Now, given the fact that the initial velocity v at 0 is equal to 1,000, plugging in t equals 0, we get 10 times 0. And let's call this C1. So we get that C1 is equal to 1,000. So now we have an equation that the velocity is equal to 10t plus 1,000. And since s prime now, which is the velocity, is equal to 10t plus 1,000, we take the antiderivative again and get that the position is equal to 5t squared, excuse me, that's 1,000, plus 1,000t plus C2. And since s at 0 is given as being on the ground, s of 0 is equal to 0, this implies that C2 is equal to 0. So our position equation is s of t equals 5t squared plus 1,000t
And to answer the final question, we want the final position in miles after 1 day. Well, T is in seconds. So we need to figure out how many seconds in a day. So T would be 24 hours in a day times 3,600 seconds in an hour. So this would be the number of seconds we need to put into the equation. And then we need to divide by 5,280 feet per mile to give us the distance in mile. So plugging into the equation, we get S equal 5 times 24 times 3,600. That whole quantity squared plus 1,000 times 24 times 3,600, and then we need to divide the entire thing by 5,280. And when we do this, we see that S is equal to 7,085,454.55 miles, which we would round off to the nearest mile as 7,085,455 miles. So this rocket really took off with this warp drive.